take all of them, the bounds, and here open bracket, close bracket, open bracket, because the first interval is 1, 4, the second interval is 2, 4. So I associate to each bound if it is an open or closed. You know, so it is a lower bound, upper bound. When it's open, it's a lower bound. When it's closed, it's an upper bound of an interval. Then I will sort them like this. So of course, the brackets have moved also. And now, once I have sorted them, I will count +1 when it's open. So +1, +1, +1, +1, and so on. -1 because the bracket is closed. -1 because it is closed, and so on. So it means that what I am doing, I am going from left to right, and when I see an open bracket, I increase 1. Here I have 2 open brackets and so on. And I am able to see here the relaxed intersection. So here it will correspond to, I will be consistent with 5 intervals, here with 4 intervals also, with 3 intervals, this one. Here with 1 interval, I will be consistent with 1 interval, and with all with 0 intervals. So what I wanted to tell you is that computing the relaxed intersection of n intervals or n boxes is easy. Even if it's not easy for us, you can see here I have 10 boxes. I want to relax 2 boxes. So of course we can see here that this one and this one can be relaxed, and the 8, if you want, the 2 intersection of these 9 boxes will be here. It's not easy to see graphically, but the methodology is simple. You project all these 9 boxes and I will obtain 9 intervals. I will compute the relaxed intersection of the 9 intervals, the x-axis, in the y-axis, and I will obtain 1 interval here, 1 interval here. The Cartesian product of the 2 intervals will give me the black box. So, what I wanted to say is that it is easy to compute the relaxed intersection of n contractors and to be robust with respect to outliers. So, since I think I have finished here. What I wanted to show is just I come back to SOSIS. So SOSIS is the name of this submarine. It has a sonar here. And it sends every 0.1 second, it sends a wave in one direction and measure a distance to the wall. The sonar is turning around like this. At each time, he has an information on the distance, and it will transform into a contractor. But something like almost half of the data are outlier, because you have multiple echo, because you have obstacles that are not considered in the map. And with all these contractors are put all together, we compute the relaxed intersection, and in a dynamic way, so it is some kind of robust, nonlinear observer with contractor, and we are able to estimate the localization to localize the robot in a real time. So just to show that it is quite efficient, even if we allow few bisections. So the robot is able to localize itself using a robust contractor approach in order to localize itself. Okay? So contractor approach can be used for nonlinear observers. But if you want them to work in a complex situation where you have outliers, which is often the case in practice, it is important to use a relaxed intersection. Okay, so now I have finished with the relaxed intersection, and I wanted to say a few words about SLAM. So first, to illustrate what is SLAM, I will explain you at the moment how we are doing without SLAM, and then I will explain why SLAM is important. So, as I said yesterday, in Brest we are working with underwater robotics, and I will present a video of a typical video of what we are supposed to do. So, ENSTA is a military school, so we have we try we try to find mines. So most of the time we are dealing with underwater robots to find mines. So why is it important in this context? As you can see here, we have a boat, and the boat, not this boat, the bigger boat, has to come back into a harbor. But the zone is not secure. Maybe there is mines. So what we do at the moment, I will show later some video, we send robots that will look at mines. Here you have several robots, but most of the time we use only one robot. But here in this video we have several pictures. So first we send Zodiac, this kind of boat, with a robot inside. It goes in the zone which is not secure, and the Zodiac, important. Then transponder. So I will show you what is a transponder, but you should understand that under the water you have no GPS. The robot is not, it will be lost. That's why we need transponder. Transponder, what's the bottom? Of course, transponder is lost. It does not know its position. But the Zodiac at the surface knows its position because it has a GPS. So you will see why we send transponder. So it takes several transponder, 3 transponder. So as you can see, here, here, and here. Now it has to localize the transponder. So to localize, it will send an acoustic wave, as I saw here. It's a range-only approach. It means that it will send an omnidirectional wave, and this one has a small program, and it will answer. So I will show you now. Wave, here, as soon as it has received it, it answers. The robot here measures the time flight between go and return. Okay, this is done for all transponders. Okay, for all transponders. So now you know the distance between the known position and the unknown position of the transponder. It will move somewhere else, and it will measure. Okay, so here it will have some distance equation, as I explained above. Okay, it knows its position. Okay, now mission planning. So some not very past planning here, but you can see that it will, since we have a swarm of robots, will decompose the zone that has to be secure into blocks. Each robot will inspect a zone. Okay? So, of course, everything is supervised by the big boat. So, WiMAX communication. So, all underwater robots will go inside the water. And, of course, it will have cameras, sonar, deployable transponder. I will explain why. Sites to find mines. The objective is to find mines. And a communication with the Zodiac, and then with the big boat. So, what is important? You can see here the old transponders. The robots here know where they are because of the transponders that are here. Okay? So, what I can see here, so this one is a transponder. It means each robot has his own transponder, otherwise they will be lost. Under the water, no GPS. Again, we'll see that maybe we'll see all of them have the transponder. Go and return. Okay, it will be able to know its position, but from this distance it will be able, so from these three transponders, it will know where it is, but it will also be able to measure other distances, so it can guess where this new transponder is, and so on. Okay, so everything, of course, has to be distributed inside the swarm. They know where they are. But transponder, we don't like it, because it costs a lot of production. We want to avoid that. That's why we need SLAM. So I will explain you after why we need SLAM. I will finish because it's a good application for what we are doing. Detection phase. Here you have a mine. With a sonar can read images. And with images, of course, they are able to see things with sonar images. So here you have a mine, here you have a mine. Of course, it comes back at the surface, so the autonomy is quite limited. You just have to survey the zone, but all decisions are taken by humans. It communicates with this one, with the Zodiac, which will communicate with the people, but all decisions are taken by the group. So the humans have decided that something in the image are quite strange, and this robot has to inspect with cameras. First with maybe with a camera and sonar also. So high frequency sonars. Again, it knows where it is because of the transponders. It comes back to the surface. It always communicates with humans for decision. Of course, what happened, you will see what happened, is that here they are waiting for the zone to be secure, but here they will take all information collected by the robots in order to find here a secure access. Of course, there is, most of the time we don't do this, we try to destroy the mines. But here, just a scenario. Okay? So now what I want to say is that which robot we have in Brest. We have, excuse me, Whoop. Sorry. Okay. At the moment, we have one more, but more and more, we want to deal with swarm because things are more easy with swarms, and cost a big robot is dangerous. When he has a mission, so here is a Rat de Brest, and the robot has a mission of about 10 hours, and he has a sonar, and he builds images, and with images, he's able to check if there is mines on it. Then, because we have some big nuclear submarines in the zone, and it has to the job of to see there is no mines, but there is never mine. Never mind. Okay. So it's not the same scenario as we did before, but it gives you an idea on which robot we are dealing at the moment.
Sorry?
Yes?
How does this one localize itself?
I will explain it. I will explain it. But at the moment, it is most of the time it is a dead reckoning approach. He has very good central, good lock Doppler, and with the dead reckoning, it knows about where it is, but the accuracy is not that good. So it can be dangerous. and we are not sure that it has inspected the right zone. So it is important to be sure, because, for instance, if the robot has to check this zone, if we do something like this, but imagine, he thinks it should do that, and it will come back. But imagine, get lost, it come back. We are not sure that there is no mines here. Okay, so it's a problem. And it is not possible for the robot to surface every 10 minutes to localize itself. So we can put better and better sensors, but it costs a lot of money, and that's why we want that. So first of all, about the control. Control algorithm for this, as you can see here, the target, submarines, we use some kind of feedback linearization method that normally we have a convergence of the robot toward the target. Okay, here it's a cycloid, but most of the time the target do something like this. As we can see here, we think the robot is on the target, but what is important is it isn't sure that the robot believes he is in the target, and its regulation is made with respect to the observer. He thinks he's in the target if he is not, but because you have an observer, because he does not know exactly his position, maybe he's not in the target. So the localization is a key point. I will not speak in this application about the control. Control can be considered as solved for this problem. Okay? So the approach, I will illustrate the approach on a reconstruction. It is a reconstruction of a mission we have done in Bay of Guarani. It was an actual mission, but it is impossible to illustrate without some kind of virtual reconstruction of the experiment. So I remove the thing. At the beginning, I represented some points, so where you think it is in blue at the beginning, and more the blue will become red. Red means at the end of the mission. It is a 2-hour experiment. As you can see, we put mines. So I will show you how mines are. I go up, I increase, oops, sorry, I go up. You can see here an idea of the mission. So the robot, it is what has been done. What I wanted to, whoops, sorry. Okay, where is the robot? So you can see mines. So red is at the end of the mission, and you can see that the trajectory, typical trajectory of the robot. Again, it's not the reality, it's a reconstruction of what we think the robot has done. After, okay. Now, I will come back to slide. So first of all, the SLAM. SLAM means simultaneous localization and mapping. At the beginning, the robot is at the surface of the ocean. It's here. When it goes under the water, here it has a GPS. Here it has no GPS, but he has a good sample, a good Doppler system to measure speeds. So the robot knows where it is, approximately. After, the precision decreases. So it's become less and less accurate. But we put here some landmarks, not landmarks, sea marks, because it's at the bottom of the ocean. And the robot can see them. When the robot sees a mark, it has an idea where it is. But an idea, he approximately knows where it is, so there is an imprecision. Now after, the robot moves, and it is more and more lost. When it comes back, it can see the mark. So it will be able to contract its position because it sees something it has already seen before. So the first step, when it was here and when it is able to localize the map, it is called mapping. When it contracts its position with respect to a mark, it is called localization. Okay, so that's why we call it simultaneous localization in mapping, because it tries to solve both problems altogether. So at the beginning, people in robotics, you have some team work on localization, some other team working on mapping in a separate way. So people in mapping system assume that the robot was localized, and people that work on localization assume the map was correct. But in fact, it was not the case. So what has been shown maybe something like 20 years ago is to show that the problem should be solved simultaneously, and it was not so difficult to do. Okay? So how do we represent the problem? The robot is described, is a dynamic system described by a state equation. We know U, X, we don't know it. So first of all, a SLAM problem is a state estimation problem. There is some measurements. What is different in a SLAM problem is that you have some equations that are related to marks. Marks here. But it's some kind of state estimation problem. So what is the interval approach for this? So it was Rederberg. What are the sensors? On the experiment at the beginning, we know with GPS where we are with a precision of something like 5 meters. Good GPS. Now, at the beginning of the mission, and 2 hours later, we also have a sonar. So sonar is able to see through a very thin window. That's why I represent here what at a given instant t the submarine, the robot, is able to see. So here through a thin window. Only on its right in this application. Okay, so I will not explain the principle of the sonar, but the robot is able to build such images. And as we can see here, the robot has detected a mine. So we put real mines so we put real mines. Maybe I can show you what kind of mines we put. So we have a lot of mines. We put several mines. Okay, all mines we have. Plenty of them. Okay. Okay, so we measure the speed. We measure, with the inertial central, we are able to measure angles, Euler angles. And after the mission, we are able, so it is done by a human operator, it's not totally automatic, but a human operator is able to look at the image and to say that, oh, here I have detected a mine. It is this mine. And I have detected here and here, so the mine number 1 has been detected here. It was at this time, and the distance to the robot was this. I have detected again the mine number 1 here, and here, and here. I have detected the mine number 0 only once, so it will not help me for SLAM, and so on. The mine number 3 has been detected here and here, only twice. And so what is a contractor approach for this problem? It's like the electronic circuit. We put all equations together. We don't care, we don't try to solve it, we put all equations. So the equations are given here. First, a link between our position in the local coordinate to the latitude and longitude. We also here equation defining our rotation matrices. We have the global rotation matrix, a differential equation. So we represent the differential equation will be used as a contractor. Here we measure some distances between the mark and the robot at a given time, and here is the distance that has been measured. Here it means that when we see a line, it is perpendicular to the robot. So the idea is not to try to find some methodology to solve the SLAM, is to take the SLAM problem and to transform into equation. The number of equations is huge because you have as many equations as you have different T and different E. So you have thousands of equations. And each equation for each T, for each I, will be transformed into contractor. So I will have thousands of contractors. And I will call them up to equilibrium. It is only what we do. And I will illustrate now on the software that is called Jaulin. I will illustrate graphically how it works on the experiment I have shown you before. Okay, so again, you can see here the beginning of the mission, and at the beginning of the mission, you can see it is moving. It is on the surface, moves with the waves. When it is, you can see, you can feel the wave. At the beginning, it has the GPS, but quickly, the robot will go down, and I will take some altitude. I will increase the size, and we can see here the trajectory, estimated trajectory with the lines. So first of all, we can try to perform some kind of interval simulation, which corresponds to a forward, to a forward simulation. So the robot is here at the beginning and is more and more lost. This is the envelope of the trajectory, which called the tube. And as you can see, at the end, the robot is almost totally lost. Now, it sees some lines. So if I contract the lines, I will contract the line here, and I will be able to see them. Okay, the lines are here. It is a precision of line, which is not accurate enough. We want to be able, so this corresponds to something like 200 meters. It is not sufficient because when we have found one, we want to send another robot, which will be able to, or most of the time it will be divers that will be able to catch the lines. But the imprecision should be something like 10 meters, otherwise it's too big to find the line. Okay, so now, again to trajectory envelope, I will perform the SLAM, so I will up to the fixed point. So I will contract forward, backward, and C marks, and so on, and I will contract up to the equilibrium. As you can see, for a 2 hours mission, in something like very quickly, okay, sorry, we are able to converge to to the fixed point. So it takes something like less than 1 minute, but it is a 2-hour mission. And we have thousands of variables. So we were able to find these boxes for the mind, and this tube for the trajectory. So the contractor approach was able to solve a large non-linear problem without linearizing. It is guaranteed, the method is guaranteed. If the assumptions are guaranteed, the result is guaranteed. There is no linearization, the method does not bring approximation somewhere. Of course, if the assumptions are not guaranteed, you will obtain a result which is not guaranteed. Okay, so it is guaranteed modulo the assumptions. Okay. So that's all about the SLAM problem. I wanted to be fast, but just to give you an idea that it can work for large dimensional problems. And you have other methods for this. You can also use a Kalman filter. Okay, Kalman filter give you something like this. So it works quite well, but you have some linearization. The Kalman filter takes more time because for this, I think it took something like 3 or 4 minutes to get the envelope. So it takes more time than the contractor approach. Okay, so that's all I wanted to say for SLAM. If you have any question.
Sorry.
Yes?
In your project, I think that you don't assume any disturbance, because if you have a disturbance, for example, your robots, there is a ocean waves or any disturbance that they have.
Yeah.
So when they measure the distance, there is an error here.
Yes.
Because, but I didn't see that you assume any disturbance.
I think when I measure something, the disturbances are inside the intervals. They are always inside the interval. When I measure a distance, I will say, in the equation, I measure distance with a precision of 1 meter.
Okay.
All disturbance, even when
but this is not realistic that you said 1 meters, because we don't know how, you didn't measure the disturbance that moment. For example, the robot's here, but the ocean waves comes and the robots comes here. So, the distance is so different.
Yes.
So you cannot say, okay, I assume that 1 meters for the error. This is not realistic.
I think maybe it's not always realistic, the assumption. What we say then, that we have some assumption and we will solve with respect to this assumption. The assumption may be not realistic. Of course, we try to do them realistic. But I think for this kind of application, when you measure, we measure a distance of 1 meter, it is true. It is it corresponds to the distance with a precision of 1 meter. But of course, sometimes we'll have outliers. We can have outliers. The main problem is outliers. Not, and of course the model is, we assume that the state equations are satisfied, but the state equations are not always satisfied. For instance, we did not take the currents into account.
Mm-hmm.
Maybe we should have done it, but it's, the problem is that we have something more and more complicated, and it's difficult to know in advance all equations.
And early this morning, when you explained the equation, for example, you said x1 plus x2, and that you calculate the contract. But in real world, we have nonlinear and differential equation or something like that.
Yes.
When you have differential equation, how you know that? What's the, when you said, for example, x1 plus x2, so these are in the, for example, between 1 and 2.
Yeah.
Do you get what I mean? And in the morning that you have some slides about that. So when you have a differential equation, how you know that what is this area that...
Okay. So maybe I did not explain it, but when you have a differential equation, okay, x dot equal f of x. Something like this.
Exactly.
If you know where you are, at time, if you know a box where you are at time 0, so it is, there is, we can integrate. So of course, if you know the point, if you have a point, you can integrate using, for instance, a Runge-Kutta method. But the Runge-Kutta method or Euler method is not guaranteed. You know just that if you will converge, you take a step which is very small, you can have some convergence properties. But there is some special method with intervals, I did not explain them here, but you can integrate this box and to find a box where you can guarantee that all at time t, you will be in zero. You can guarantee that. Of course, this has to be true. It is with respect to this equation. So it is a lot of work has been done like this, on this. A lot of mathematicians are working on this topic. So it is guaranteed integration, interval integration. And you have a library called VNode, a big library which is devoted to this problem. And the most famous algorithm is the loaner algorithm, but I did not explain it here. So it's guaranteed integration, and it's what we do here. Okay. Okay, so now I will discuss about control. Okay. Okay, so and I will illustrate what we can do with control using sailboats, because in Brest we have to build sailboats, and sailboats is a very interesting nonlinear system. Easy to build, typically nonlinear. So we started with sailboats with a long time, maybe 5, 6 or 7 years ago. So it is our first boat. And we made 6 years ago a small experiment across near across the Rat de Brest. And since we tried to cross the Atlantic Ocean, but always have problem. So now, but it's interesting in an academic point of view, because first of all, a lot of people in Brest copy us, because we have 5 engineering schools. So all of us are building robots. So here it's a robot of École Navale. And maybe we have something, almost 10 sailboat robots in Brest. That's why next year we organize a conference, big conference on sailboat robots, WRSC. Last year it was in England, in Cardiff. Okay. So the robot which is I want to discuss is Vemos. This one, the most famous. It's very, very famous. If you Google Vemos, you will see a lot of pictures on the TV, on a lot of newspaper. Okay. So Vemos is here. It is a nonlinear system with sensors. So here it's a GPS, but it's also a wind sensor, a compass also. You have electrical controls and so on. So first of all, for us, a robot is, or a sailboat, is a state equation. So a state equation, let me illustrate here. Okay, so a state equation describes the dynamics of the system. So for instance, here you have the boat and a state equation. Okay, you can see the boat moves. There is 2 inputs. The rudder, see the rudder. If I move the rudder like this, for instance, you will see, stop, it's a minute. Okay? There is another input, which is the sail. So the sail is, here is the wind. And you can see here, the sail behaves like a flag. Here, will enter inside the meter. Okay, so you see, look, you can guess. Typically, the state equation describes the dynamic of the robot. It's not guaranteed, but we will assume that the robot is described by such nonlinear equation. So I do not present you the model here. Oh, excuse me. Okay. So first of all, if we had a controller of this form, then the system becomes autonomous, and we have a differential equation. Okay. Now, okay, differential. Now we have uncertainty. So because we have uncertainty, we cannot write anymore x dot, so the state will be exactly equal to f of x. Because we have uncertainty, so the uncertainty can be noise, can be whatever, we will describe it by x dot belongs to f of x. Okay, so if you have here the state space, if you are here, correspond to x1, x2 for instance, you have here f of x, and here you have x. Now, it is not exactly like this. You have a lot of possible direction, and this is what we call a differential inclusion. Okay, so what we want to prove is that controller we have, the differential inclusion will satisfy some stability properties. Okay, stop me if I... Okay, so now, what is the approach? The Sable has two inputs. The first input is the angle of the sail, but not exactly the angle, and the rudder. The rudder is in the back, okay? And here is the maximum angle of the sail. Why? Because if I have the robot here, if the wind come from here, the sail, so here you have the rudder, here you have the sail. The sail is like this, and here you have the main ship. Some kind of rope between the center of the boat and the sail. So here, if it is, I just control the length of the main ship. So I control the maximum angle of the sail. But the sail can be like this. If suddenly, like this, without changing the input, the sail will go like this. Okay, so you should understand. Now we'll have a different kind of controller. The controller will have a low-level controller that will tune the rudder and the sail with respect to heading that we want, theta bar. And then we have another controller that will give you theta bar, so the direction to be followed, in order to follow a line. So what we want is that our robot follows a line. Okay? So it's not, I will first speak about the heading controller, the low-level controller. Just to, it's not so I will detail this. Okay, so first, the rudder. How the rudder it works. Very classical. We compute the error, so if the robot is here, for instance, and he has a heading equal to theta, but he wants to go with this heading. So we compute the error between the actual heading desired heading. It is error. But to avoid the problem of 0 to p, the problem of modulo to p, we will filter this error through the sign. It means if I add 2p to theta to theta bar, then the error filtered by the sign will not change. Okay? It's important to put the sign. Otherwise, we have the problem with the 2p. And then it is the maximum angle of the robot. So there is two cases. Like here, it means if it is like this, I will put the rudder like this. If I am like this, I will put the rudder in another direction. But if I am in the opposite side, I will put my rudder at the maximum. That's why here, when I have approximately in the right direction, I will perform what we call a proportional control, proportional to the error. But when we are in the wrong direction, as here, I want to go there, we'll perform a bang-bang control. So, bang-bang, full on the right, full on the left. Okay? Classical in robotics. Okay. Now the same is to be a little bit saner, but we look at the difference between the desired heading and the direction of the wind. And then what we call a cardioid model, this, which tells you how to open the sail. It just means that when the wind comes from the back, you open the sail at the maximum. When you are in front of the wind, you close the sail as much as possible. I will not explain, just to tell you that there is no control theory, it's just a pragmatic approach to find a controller for this kind of system. Why? Because there is two types of systems. There is complicated system like I would say maybe the inverted pendulum or the Segway or that have been built in order to be unstable. And there is some system like the Sable that have been built since 1,000 years. And they have been built so that they are easily controlled by human beings. So most of the time we know how to control them, and we don't need big theory to control the Sable. We just try to put, we already have the control. So the first step is theta bar is the desired direction. There is a line, and we want to follow the line. When we are here, we ask the boat to go in this direction. When we are here, we ask to go to this direction. Okay. So we have the vector field we want to follow. Now the problem with this vector field is that if the wind comes from this direction, the robot will not be able to go against the wind. Okay? So there is some kind of no-go zone, which is represented here, where the robot cannot go if the wind comes from this direction. So it can go here, it can go here, it can go everywhere here, but it is not allowed to go here. Otherwise, it will not work. Okay? So some of them are not visible. So what we do, usually the method is quite simple. I've represented here, the wind is in red. The wind. It is a vector field. We want to follow this line. Okay? And you will see the blue line means that we want to be inside this corridor. So the approach to follow is the following. Is if I move, you can see the wind, then some direction become unfeasible. These one are feasible, but these one are unfeasible. So what we do classically, we want to follow a direction, but this direction is not possible. What we do? We have to go either in this direction, either in this direction. We can choose between this one and this one. So here, because we want to follow this corridor, we choose this direction. So let me show you how it works. This direction becomes visible, and because it corresponds to this direction. And when I move the wind, you can see the field is moving in all directions. So because of the uncertainty, which is the wind, the robot will be described not by only one